Okay, let me start. So the from now on, let's discuss the what is the basis for the subspace. Okay, so the basis for the subspace H of Rn space is a linearly independent set in H. Linearly independent set in H that span H. So So, what does it mean? So, the basis, by only using the basis, we can generate the space H because the basis is the linear independent set. So, we can span the every space H by using the linear independent set vectors, right? So this is the definition of the basis. Okay, so let's see the what is the basis. First of all, in example, the columns of an invertible n by n matrix, form a basis for Rn because they are linearly independent and span Rn space. How can I do that? Because this is by Emoto matrix theorem. Okay, so if we go back to the our lecture 5.3, there was the Emoto matrix theorem, right? So there are so many statements, right, in the Emoto matrix theorem. Then we prove that these kinds of statements are whole true or whole false. So they are whole equivalent, right? So from here, matrix A is an invertible matrix. Then matrix A, the columns of matrix A span the Rn space, right? And the columns of matrix A form a linearly independent set, right? So from this Emoto matrix theorem, the immutable n by n matrix is the basis because they span the Rn space. Okay, so this is one example of the basis. And one such matrix is the n by n identity matrix. Identity matrix whose columns denote the E1 through the En. So we already talked about what is the E1, right? E2, En, right? So this set E1 through the En is called the standard basis for Rn space. So this E1 through the En is the standard basis, and the E1 through the En is from the identity matrix, right? So it was something like that, right? So in identity matrix, each column vector is a standard basis for the Rn space. Okay, so this is the one example of the basis. Okay, so let's find out basis for the null space, and let's find out basis for the column space. Okay, because we already talked about what is a column vector and what is a column space and what is a null space. Then let's find out the basis for those spaces. Okay, First of all, what is the basis for the null space of the matrix? Here's a matrix A, something like that. And how can I find that? Okay, so first of all, what is the null space of this matrix? Whole possible solution set that satisfy Ax equals 0, right? The homogeneous the solution set of the homogeneous system Ax equals 0. Okay, so then what is the basis for this solution X? Then we can represent this solution X with some basis function. Okay, let's do that. First of all, the homogeneous equation Ax equals 0 can be solved as follows. In other words, A and 0, this is the augmented matrix, right? So we can row reduce this augmented matrix to the following echelon form or the reduced echelon form, right? So by using the row operation, right, then we can row reduce this original matrix, something like this. Okay, so you can do this by yourself, right? Then anyway, we have the reduced echelon form of the this augmented matrix, right? Okay, so this column is related to the vector value x1, x2, x3, x4, x5, right? So when vector x is the x1, x2, okay. Let's use just colorful. x1, x2, x3, x4, x5, right? Then what is the pivot column here? What is the pivot column? What is the pivot position? Here, right? So what is the pivot column? Here and here. So x1 and x3 is the what? And so first of all, x2, x4, x5 are what? They are free variable, right? Then x1 and x3 are what? Basis variable. Basic variable, right? It means that x1 and x3 is the basic variable can be represented in terms of the free variable, right? Right. So let's find the general solution in the parametric vector form. Okay. So first of all, x1, x2, x3, x4 is equal to 2x2 plus x4 minus 3x5. Why? From here, from this row, from the first row, x1 minus 2x2 minus x4 plus 3x5 equal to 0, right? So from here, we can represent the x1 in terms of x2, x4, and x5, right? Right? So from here, x1 is look like that, and x2 is the free variable, right? Then x3, something like that, from this equation, from this row, right? And x4 and x3 is a free variable, right? And then if we extract the x2 from here, the one column vector is something like that, right? And if we extract the x4 here, the remaining vectors something like this. Finally, okay, let's use this color. Okay. If we extract x5 here, the remaining vectors like that. Okay. So let's say this is a vector w, and this is a vector v, and this is vector u. Okay. So we can represent the solution x as a linear combination of the arbitrary vector u, v, w, right? So this is a general solution in parametric vector form, right? Then null space A means the solution of all possible solution x, right? The null space A is the set of the whole combination of the u, v, w from here, right? So also these three vectors are linearly independent, right? Because this x2 times u plus x4 times v plus x5 times w is equal 0 only if x2, x4, x5 is 0. Why? If we checked here, 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 to make these values as a 0, 0, 0, 0, 0, this term also should be 0. To this, x2, x4, x4 is also should be x2, x4, x5, x5 should be also 0, right? So because there is only trivial solution, so this is a linearly independent set. Okay? Okay. So, okay, this U, V, W are linearly independent. So it means that U, V, W span on null space A. Okay? Okay? So in other words, U, W, V is the basis for the null space A. Okay? So the linear combination of the U, V, W span the null space A. Okay? So this is the basis for the null space. Okay, what about the basis for the column space? What about the basis of column space? The problem was to find the basis for the column space of the matrix B, something like this, okay? Okay, so how can I find out the basis for the column space? Okay, first of all, denote the columns of B by B1 through the B5 here. So this is the B1, B2, B3, B4, B5, right? Then from here, from the relationship between B1, B2, B3, B4, B5, first of all, okay, let's see that. First of all, we know that P3 actually this this is the column vector, right? So this is the basic variable, and these two terms are non-column vector and non-pivot vector, right? So B3 can be represented by negative 3 times B1 plus B2, right? From relationship this one and this one, right? What about V4? The vector V4 can be represented by 5 times B1 negative V2, like that. Okay, so this is the V3 and V4, right? So we already know that B3 can be represent B1 and B2, and B3 can be represent B1 and B2 term, right? And B2 term. Okay. So any linear combination of the P1 through the P5 is just a combination of the P1, P2, P5. Why? Because the linear combination of a P1 through the P5 is that x1 P1 plus x2 P2 plus x5 P5, right? Then P3, if we replace the P3 and P4 here, then blah 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 P1 blah blah P2 blah blah P5. Okay, so we can represent the linear combination of the P1 through the P5 as only using the P1, P5, P2, P5. Okay. In other words, the column space can be a linear combination of the B1, B2, B5, right? So in other words, the B1, B2, B5 is the basis for the column space of B. Okay? Okay, so in general, actually this was the pivot position, right? Pivot column, right? So the pivot columns of matrix B form a basis for the column space of B. Okay, this is a really important theorem. So okay, importance the finding. So if we find out the where is the pivot columns, then we can determine the basis for the column space of B is just the pivot columns. Okay, from here. Okay. So to conclude, the matrix A is the low reduced to echelon form B. Okay, if you see this one, actually this is the echelon form, right? Echelon form or a reduced echelon form, right? It means that there might be some matrix A which is low reduced to the echelon form B, right? Then the columns are dramatically changed, right? Because by using the row operations, we introduce the echelon form, right? So the columns are dramatically changed, but the equation ax equals 0 and bx equals 0 has the same solution set, right? So we already know that by low reduced A to B, ax equals b and bx equals bx equals 0 has the same solution set, right? Same solution set. So it means that the columns of the matrix A has a exactly same linear dependence relationship of the columns of B. So what does it mean? Okay, let's say matrix A is something like this, and matrix B something like that. Then B is the reduced echelon form of the matrix A. Okay, by low reducing. Okay. Then the solution X. Okay, if we have a solution X, it represents the linear combination AX, X, and AN equals 0, right? Then this is a linear dependence relationship, right? Then because this solution X is the same to vector B, column space B, right? So x1 p1 plus xn pn is equal to 0, right? So it means that from these x solutions are same, so the linear combination or linear dependence relationship between the column vector A and column vector B are exactly same. Okay, so we will use this property from now on. So actually this was the reduced echelon form, right? So the original matrix was here. So A is a column vector A1 through A5, something like that. Then by low reduce, we can get the matrix B here, right? So you can do this now by homework, right? So anyway, we already know this matrix A is rule equivalent to the matrix B in above example. And in this case, find the basis for the column space A. Okay? So we can solve this like this. Okay, so first of all, A and B is a row equivalent. So the solution set is the same for the AX equals 0 and BX equals 0. Okay? So the following still hold true. What does it mean? So from here, the linear dependence relationship are same between A and B. So there was a linear dependency among the vector B here and here. So the column vector A also has the same linear dependency. Okay, so and A1, A2, A5 is also linearly independent, since any dependence relationship among the A1, A2, A5 would imply the same dependence relation among the B1, T2, B5. Okay, so from here, right? We already know the B1, B2, B5 is linearly independent, right? Linearly independent, right? From here, right? Then A1, A2, A5 is also linearly independent. Hence, the basis for the column vector, column space of the matrix A. Okay, so this one, A1 to 5, this one is the basis. This is a basis, okay? Okay, so here is the theorem. Here's the theorem. Interestingly, okay, we only have the original matrix A, but here we don't know where is the pivot column, where is the pivot position, and where's the pivot column. But by low reducing this matrix A into the B, we can find out the pivot position, right? Then, if we know the pivot columns of the matrix A, then pivot columns of matrix A form a basis for the column space of A. So like this. So this pivot columns are basis for the column space A. Okay. So this is the theorem. Okay. So there is a warning. Be careful to use the pivot columns of the matrix A itself for the basis of the columns A. What does it mean? The basis of the column space A is the column vector, this one. Not a column vector of the B. Okay, not a column vector of the B. Okay, so please be careful. Okay, so to summarize, if we know the pivot columns, then we can find out the basis for the column space, right? Because the pivot columns are the basis of the column space of A, right? Then, in other words, if we know the pivot columns, then we can span or we can represent the column space, right? So the pivot columns are very important. The columns that encode the property of the matrix A. Okay. So this is the end of today's class. So in the third day, let's find out what is the dimension and what is the length. Thank you.